In this lecture, we must continue with our stochastic model of Arrhenius. In the end of the last lecture, we obtained the formula dqxy is equal to this expression. The sense of dqxy is the probability that a pure random chosen fiber from the sphere of Arrhenius. One moment. Our earlier picture, which we know, this one. Random chosen fiber, I don't know, maybe this one, nobody know, yeah? Random chosen fiber is lying inside of our elemental rectangle dx dy. Well, this is this probability dqxy. The areas, the sectional areas, the real sectional areas of fibers in Arrhenius sphere have different and random shape. We need to idealize such sections. So we will idealize such sections as an idealized ring. We will assume that each fiber section have the same sectional area equal to S star bar as a mean sectional area. And because S star bar is dizzy, here it is S times sigma, which we derived earlier. We imagine that this mean area have the idealized, only idealized shape as a ring. Then such a ring have diameter d star. Maybe this diameter will be a little higher than this idealized diameter than the real diameter of the fiber. It is valid that d star bar is pi d squared by 4 d star. From this, d star is this here, so that this here, so that this here, but this is d. So that d star, it is a fiber diameter d times square root of our parameter sigma. It's a little higher than radius diameter d of fiber. And then from S star bar we can write S times sigma. Now let's go a little back to this picture which we know from last lecture. Let's imagine some light beam, some orange light beam, which is lying on the cross section of our yarn include Arrhenius sphere. This orange light beam. How is the probability? We will solve the question. How is the probability that this light beam will pass through the yarn without some problem with hindrance of fiber? How is such probability? We idealized, here is some strip, a light green strip, which is also here as a light green shown. We idealized the cross sections of fibers in Arrhenius sphere as a rings having diameter d star. Let's think, how is the position of section of fiber, ring diameter d star, for hindering or no? If fiber section have its central point. In the distance no far from d star by 2, like this here, or this here, then light beam have not chance to go beside the yarn, stopped. When the fiber have its central point outside of this light green strip, like this here or this here, then a light beam can go without problems beside the yarn. Yes. So we can formulate now the probability that the center of the randomly chosen fiber lies in the infinite long green band. How is the probability that one random chosen fiber, beta fiber section, on the center of this one, is lying inside of our light green strip, thickness lying on the distance x from yarn axis, plus minus d star by 2, and length for minus infinity to plus infinity. Yeah? Like was in our earlier picture. How is this probability? This probability we called Q here. How is the probability that random chosen fiber will be inside of our light green strip? This fiber can be can have its central point here, or here, or here, or here, in each points in our light green strip. Yeah? I said here, or here, or it means probability of this plus probability of this plus probability. Yeah? You know it from theory of probability. So that the probability is sum of probabilities dqxy, where x is going from some value x minus d star by 2 to x plus d star by 2. You here? And y is going from minus infinity to plus infinity. Is it so? Yes, it is. So we must integrate it, because don't problem with alphabet of integrating quantities, integrating variables, then and borders. Then we rename integrating variable to t. So we obtain this is our equation for qxy, and we must make this double integral. We then obtain we the value q. This value q, the sense is known. It's a repetition to our equation for our last slide. We can write in this form, or formally also q is 1 by nh times integral of this bracket times dt, where this bracket we call ft, and ft is this one. Yeah? The same. This integral we can a little rearrange. Let's use some substitution. Y, which is here, y is t times tangent alpha. Alpha is only substitution, is name of substituted quantity. This alpha have not some special logical sense. It's possible use, I don't know what, alphabet which you want. I used alpha. Yeah? So alpha have not some special interpretation, logical interpretation. It is only the variable used by integration as a substitution, yeah, method. Using this, after rearranging, which you can quietly study home, we obtain the final expression for our function f, also in such form. Well, we know Q. Once more, Q is the probability that the random chosen fiber have its central point inside of our light green strip. How is the probability that the random chosen fiber will not have its central points in our light green strip? 1 minus Q. Well, and how is the probability that no one fiber from Hyrene sphere, in the cross section, let's imagine it, will not its central point inside of our light green strip? This is probability that the first fiber is not there, and in the same moment also the second, and in the same moment also the third, to NH fibers. So we must multiply each probability of each section is 1 minus Q times 1 minus Q times 1 minus Q, and we must do it NH times, so that it is this probability that no center of any fibers lies in the infinite long green band is 1 minus Q power to NH. The probability that our light green strip is free for light beam is probability P, which is given by this. Yeah? What we obtain using Q, this here. What is F? F, we know this function F, yeah? This here. Difficult to rearrange it more, but all will be easy when we will assume that number of fibers in Hyrene sphere is relatively very, very large. Why? It often is. It often is. The traditional yarns have a lot of fibers in sphere of Hyrenes. Why? From point of view of mathematics, in a basic course on this university maybe, of mathematics, you used also one formula for limitation. It was 1 plus constant by x, brackets, power to x, if x is limited to infinity, is e power to such constant. It's one of known formula from basic course of mathematics, mathematical analysis, in the part of limits. What is structure of this problem? 1 minus some value by NH power to NH. If number of fibers in a Hyrene sphere is very large, then this probability is roughly limit of this expression by NH limited to infinity. Yeah? Have the structure of the limit. Is this step clear? Then roughly we can write P is equal roughly limit of this, and this is exponential function. It's e power to minus this integral. So P is e power 2 minus this integral. Then minus logarithm P is this integral. So we give back our structure of function f now. And after rearranging, which is here on this, we obtain final expression here. Let's continue here. Minus LP is this here. Yes. We know that S star bar is pi d star squared by 4, so this is equal to this. Both are valid. then it is valid rearranging of this parameter here according this rearrangement trivial to this form, and we can write that minus logarithms of probability, which is p, is given by such equation, where two parameters must be known: h, half decrease interval, length of half decrease interval, and c, which is the second characteristic, which is related to packing density, which will be shown later. It is also valid this here in this note is shown, so that nh must be this, only rearranging of earlier equations. Well, we have all what's necessary for our model. We had it too. And we start to compare these results with experimental experiences, based on a picture of the yarn in microscope, then image analysis technique, which you know, which is here too, I hope. And sorry, this model wasn't too precise. The question was why? So nice model, isn't it? Our models are every time nice. Okay, why? We had experiences, subjective experiences with a lot of pictures of yarn. And we knew that in the small area near to yarn surface are different small, how to say it, loops, maybe loops, short ends of fibers and so on. And this type of fibers create something like a mousse on the yarn surface. There are fibers of one type. Another fibers was long flying, free-flying fibers, which bring complications into following technology and so on and so on. So that, maybe this is the problem. Don't exist only one type of fibers in the sphere of high-Raynaud. It exists two types of fibers which create both types together, the final effect of high-Raynaud. Yeah? One type create at most something like, subjectively say, mousse on the surface of the yarn, and second type of flying of single fibers. Well, let's imagine that we have on the surface in the high-Raynaud sphere two types of fibers. Yeah, two types of high-Raynaud. Let's imagine as a red fibers and blue fibers when you want. Yeah, all together are created the effect of high-Raynaud. One type of fibers as well as the second type fibers follows our model, but with quite other parameters. Both follows our model, both type follows our model, but with quite different parameters. Then we can very easy to define a double exponential model. We call the earlier model as an exponential model because it was seen that the number of protruding fibers have the exponential decreasing tendency, yeah, in earlier model. Therefore, now we speak about a double exponential model. We use symbol. One type of fibers have general symbol I. The quantities for one type of fibers will have same subscript I. Common parameters, they will be without subscript. and the resulting values also without subscript. Well, common parameters are RD. It's one yarn, same radius, RD, yeah? Common parameter is also D star, because we said the distribution of directions of fibers is independent to position of the fibers, so also D star. Common variables were also the variables R and X, radius of differential and distance on which is going the light beam. Parameters following any type are mu d, packing density, starting value of packing density on the yarn body. It is packing density for first type of fibers and for second type of fibers. Mu and hi is half degrees interval, which is other for first type of fibers and for second type of fibers. And also the parameter c. We derived this equation, and here you can see here how is the structure here. Parameter c, ci, related to hi and packing density. Yeah, starting value of packing density and the quantity hi. So, number of fibers protruding for radius through type, ith type, first or second, yeah, this is our known equation. Only on the place of m is now mi, on the place of md is mdi, because this related to first or second, generally ith type of fibers. Yeah. Similarly, packing density at radius are our old equation with subscripts on the quantities which are related to our type of fibers. Number of fibers in the whole Hyranis region is this here. Same idea, only a subscripts I. And our probability, which is probability of B free, our green strip for light, from fibers of ith, means first or second type. Yeah, is this here. Now, how is the resultant variables for both types together? Number of fibers protruding radius R. It must be number of fibers from first type plus number of fibers from second type. So M1 plus M2. You obtain this here. Yeah? Especially total number of protruding fibers, the cylinder of compact body yarn, MD, it's MD1 plus MD2. From starting position are going out red as well as blue fibers when you want. Yeah? Well, how is packing density? The same. Packing density is the packing density from the first fibers plus packing density from the second fibers. It's evident, it's trivial. So mu is mu1 plus mu2. Using this, we obtain this here. Special case on R equal RD, starting radius from Hyranis sphere. Mu is mu d, and it is sum of mu d1 and mu d2, evidently. Number of fibers in the whole Hyranis region, it is the same. It must be sum of both. Same logic. Then it is this here, using our equations, yeah? A little other is the question about the probability. How is the probability that the light beam passes without any obstruction by the yarn at the same distance x, without problems? It's a probability that no one red fiber is in disturbed in our light green strip. And in the same moment, also no one blue fiber must disturb there. Yeah, both together. Both situations must be together. How case it is from theory of probability? It must be this and this also, both together. It is we must multiply the probabilities so that the the final probability P is P1 times P2. Now it is evident minus logarithm is this here. Using our equations we obtain this expression where C1 and C2 are this here. So we for this solving of this probability we need for parameters C1 H1, C2 H2 and or mu D1 H1, mu D2 H2 because C is given all this and this. Well, and the complementary probability that the light beam cannot pass at the distance x from the yarn axis, it must be 1 minus p. P is function of x, therefore in this moment I write p as a function of x. Yeah? Such function cannot pass. We call as a blackening function. This is a blackening function. And how is this this function? How shape have this curve of such functions schematically? It is shown on the picture. The blackening, in the central part of the yarn, this is yarn radius from 0 to infinity, to long lenses. This is the blackening function. In the center we see only black points. Then it is this blackening function is equal 1. And then more and more with increasing of x, more and more light beams are passing beside the yarn. Then the blackening function is smaller and smaller and smaller and limited theoretically in with x limited to infinity, it limited to 0. On some radius RD started the hemisphere. So for us is actual only this. We create a model for this part. This is only extrapolation. It is not too important for us because it is the body of the yarn and there are valid another regulations. Well, this blackening function, I must also in short comment, I want to comment some integral characteristics. Because now the blackening function is a function. But sometimes we need to have some scalar quantity which characterize intensity, or how to say it intuitively, of hairiness. We can say that it can be, for example, area under our blackening function. So it is integral of our blackening function. Yeah? Then it is scalar value and it can be some characteristic of scalar characteristic of hairiness. We can also separately characterize similarly how is the effect of the first and the second type of fibers. We can also, based on this of our equations, define diameters, yarn diameters. In my department, we use two different definitions. Here is as the first cover definition. We can say that we will call as a yarn radius, 1/2 of yarn diameter, such radius on which the blackening function value is 1/2. It means 1/2 of points is black because fibers in microscope, and second half of point is white because light. Yeah? This definition corresponds to the idea of covering. When dominant is the black points, then we feel it as a yarn based on our eyes. And we can say this is yarn, for example, in woven fabric. and vice versa, of course. Yeah. So it is shown how to work. We usually use this constant 0.5, I said it. The second definition is the definition based on the packing density. Professor Richtiak often used this definition, and we use this definition also. Based on my meaning, the cover definition is sometimes better for application by construction of woven fabrics. The density definition is better for study of the internal mechanic of the yarn. What is the density definition? The density definition is that the radius on which the packing density have given value, this is our radius. There are different possibilities, but usually this quantity is given between 0.1 and 0.15. It means 10 to 15%. Earlier I used 0.14, means 14% as a criterion for diameter. Now maybe a little smaller value, 0.11, not too important for practical point of view. And using our equations, we can define in which moment, in which radius, especially this value is. Well, this is theoretical concept of hairiness. Of course, I don't know a whole literature which is in the world. Nobody knows it. Nevertheless, I don't meet one publication with an alternative theoretical model, probabilistic model of hairiness. As empirical models, you have a lot. Therefore, this is for me the best, because I don't know the second version. Okay. Now, quickly to the experimental method. Our experimental method is very easy in principle. Yarn is going through microscope. On the microscope we have some camera, CCD camera, and the picture is we obtain on the screen. We apply on the like this here, yeah? And in this row of pixels we can say we define the center of this black part as a yarn axis, and then to both sides we can say in which distance is black or white pixel. Yeah? When we repeat it lot times from lot of pictures of the yarn, we can construct experimentally our blackening function. I think it's clear. For example, in small distances, practically 100% of points is black. Maybe in such distance, sometimes black, sometimes white, maybe near to 0.5. In, I don't know, in this distance, 100 times white and 1 times black, yeah? Very small value of blackening function. So such blackening function is possible using, of course, it needs some manipulation, it can some binary segmentation and so on of our picture, yeah? But it is only the know-how of our experimental method. And then we obtain experimental curve. This slightly sawtooth curve is an experimental curve, experimentally evaluated curve of blackening function. And using such parameters, we obtain theoretical curve. You can see that with 4 good chosen parameters, our theoretical model follows our experimental result very, very good. We can divide our result to 2 parts because we speak about 2 types of fibers, and in most volume of our yarns, is very high differences between these two types of fibers. It is shown also here. The starting packing density of one type, we call this as a dense component, is started on the yarn surface in a relatively very high value of packing density. From starting cylinder of yarn body, lot of fibers are going out. So number of protruding fibers in a cylinder of yarn body in the first group, this dense component fiber, is very high, but they are short. So number of protruding fibers through this type of fibers is quickly decreasing, is reduced to 0. In this example, it is this curve. Started in a high value, but quickly decreased to 0. X coordinate is 0. The second type of fibers, we call it as a loose component, started on the starting cylinder of yarn body with smaller value of packing density. It means no too much fibers is going out from the second type, but number of these decreased slowly. So that when some fiber is starting from cylinder, then it usually is very long, finished on the very long length. It is a called loose component. Some first results can see it. See, H1, H2. H is half interval of decreasing of number of protruding fibers. H1 is 0.00, maximum 0.1 and something. Yeah, here is 0.02. In opposite to them, H2 is much more higher. Yeah? Values H2 are much more higher than the values H1. The interval of second loose fibers is half decreasing is much more higher. Long flying fibers. From other side, packing densities 1 and second starting value, D1 is much more higher than D2 for some set of different yarns. It means starting number of fibers is much more higher, but quickly are going down, group 1, and the second group it is in opposite. Some graphs. We have much more graphs. Mrs. Krupintsova is working on this field in our department. Very, very good. We can also evaluate some scalar value, this red area under our curve, this integral. This is one example. On abscissa of this graph, okay, first on the left-hand side to right-hand side, there are two diameters, the core and the dense, evaluated from our model. You can see that the correlation is very, very high. It is possible we mentioned that it will be so. Interesting is the second diagram, best of my meaning, very interesting. This is Usta hyrenis. You know that Usta, I shall say, Zellweger instrument produced in the Swiss town named Usta, because Usta is name of town in Switzerland. The company have the name Zellweger, but in the whole world it is known as a Usta instrument. So I will call it Usta instrument. In Usta instrument is possible measure also hyrenis, some value of hyrenis. This is measured value by Usta, and this is our integral from our curve. You can see that the correlation is 0.99 correlation coefficient, very high. So our method gives the very proportional result than Oster method, but we obtain also whole curve in relation to radius, how is decreasing the high-riness, and we can divide whole high-riness to two parts. This mousse part, intuitively say, and the part of long-flying fibers. Therefore, our method, we mean that it is can deeper analyze based on our theoretical model, which I presented in our last lectures, can deeper analyze the phenomenon of high-riness of the yarn. Well, and this is all. I'm sorry that today's couple of, or the last two lectures was a little difficult for you, but not too much. Only we used more the known laws which are valid in the theory of probability, isn't it? Well, thank you for your attention.